Hello gang, today we're going to be talking about some of those unanswered questions that you might have from calculus. So back in the day when we were talking about the power rule, specifically with antiderivatives, we really harped over the idea that n was not allowed to be negative 1. If you had an integral such as the integral from a to b of 1 over x dx, and my n is negative 1, the power rule did not work, mostly because when you add 1 to negative 1 it becomes 0 and you can't divide by 0. Today we're going to analyze this a little bit more and see if our newfound skills with logs can help us answer the question. So our story begins by taking a look at this guy. And here's a picture of 1 over x, this function right up top. And what I want to do is I want to draw its antiderivative. Again, remember I can draw my antiderivative by letting the y value of 1 over x be the slope of this line. As I draw my antiderivative, it kind of comes over. Notice the fact as these y values get lower, my slope starts to approach 0 as it's going across. And this red graph cutting through here looks pretty familiar to me. It's actually very similar to what we were talking about the other day with our graph of ln of x, which means that logs allow me now to find the antiderivative of 1 over x. It has a different x-intercept simply because the c value can shift it up or down. So here you go, our formal definition. The integral of 1 over u du is equal to the natural log of the absolute value of u plus c. That absolute value simply hinges on the idea that you're not allowed to put a negative number inside a log, so the absolute value ensures that we always get a positive number, and that solves our problem. So to use this, here we have an indefinite integral. If we want to try and figure out what this is, we have to force it into that format. So we get to use our old friend, substitution. So if u equals x minus 2, then du is going to equal dx, and then I have a nice even trade. So I have 5 over u du, and when I want to integrate that, the 5 is a constant, it just comes along for the ride. 1 over u, we just learned, is the natural log of the absolute value of u, and then I put a plus c on the end. As usual with substitution, we then trade the u back. Easy peasy. Now I got myself an answer. So ultimately, we now have a new spot for u. U really loves to be inside parentheses. U really loves to be bottom of the fraction. Those are two of my favorite hiding spots for u. That's where I tend to look first. If I don't know how to do the problem straight up, I go to look in those spots. Later on in the week, we're going to learn a third hiding spot for u, but for right now, that's good. So here we have a definite integral. Same game though, I just want to use fundamental theorem, and to use fundamental theorem, I have to find an antiderivative. So again, I'm going to look in that denominator of the fraction to find myself a u. I'm not 100% certain this is going to work, but this is the first place I want to go looking to see if I can solve the problem. When I set it up, that 2x up top is unaffected. The bottom is now u, and my dx is now du over 2x. Look at that. The 2x is crossed out beautifully, and now I've got 1 over u du. So my integral of 1 over u du is now going to be the natural log of the absolute value of u, and instead of plus c, I'm now going to put a 0.3 on the end. So I've got the natural log of the absolute value of x squared plus 3, evaluated from x equals 0 up to 3. I'll throw them right on those absolute value bars. All right, so throw 3 in there. 3 squared is 9, plus 3 is 12. Throw 0 in there. 0 squared is 0, plus 3 is 3. So that's my answer. If I'm feeling a little bit fancy, I can use my log skills to say that subtraction of logs is division of the innards. So that's the natural log of 4. It is a number. I was expecting a number because it's a definite integral, so I'm good. All right, so here we get a similar problem. I could pick my u and x minus 5. I'll go about my business. Everything will be happy. I'll feel good about my answer. Life's wonderful. And then I realize I've got a slight problem. If x equals 5, that means that I'm going to have a vertical asymptote. A vertical asymptote means that my graph is going to have a skip at 5, something along these lines. And the problem is I'm trying to go from 1 to 8. So if I'm trying to go from 1 to 8, this area here is infinite, and this area is infinite. So because I've got this skip in the graph, fundamental theorem does not work. So I've got two options. I can either give up and walk away, or I could try and use fnit to approximate the area. I'm going to choose the first one. I'm going to say fail, and I'm going to walk away from the problem. Alright, so here again I'm a little bit paranoid, but I don't have a 0 in my region, so I'm happy. I don't even need substitution because I've got this classic 1 over x. So I go straight into natural log of the absolute value of x, evaluate it from -3 to -2. I throw a -2 in there, the absolute value turns it positive, and I get the natural log of 2. I throw a 3 in there, and I get the natural log of 3. And again, I can pretty that up a little bit and say the natural log of 2/3. Alright, this one's funkier. It's calling to mind some of the things we talked about earlier in the course. Remember, area under the curve is integral. So this shaded region right here is essentially asking me, what is the integral from 0 to pi over 3 of tan x dx? Immediately I'm going to go to my list of 6 trig derivatives. That's not on my list. I know the derivative of tan, but I don't know the integral of tan. So now I need a new plan. What I could do, switch it up a little bit, call it sine over cosine. Now in the past, this was not at all helpful because I just traded one dead end for another dead end. But now that I know that fractions are viable, I can let my u be cosine x because I love my u to be in the denominator. So du is going to now equal negative sine x dx. dx is now going to equal du over negative sine x. And now I think I've got a viable trade. I've got a sine x over u times du over negative sine x, and those sine x's are now going to cross out. So I picked up a negative in the exchange, but other than that, this looks like my classic formula, 1 over u du. So now I've got negative natural log of the absolute value of u, evaluated from 0 to pi over 3. Trade that u back. Natural log of my u is cosine x, going from 0 to pi over 3. Cosine of pi over 3, what's that going to be? Root 3 over 2? So I've got negative natural log of root 3 over 2 minus cosine of 0 is going to give me 1. So minus negative natural log of 1. And I can either let it stand like that, or I can combine these guys together. Be careful combining these guys together because I've got this negative 1 out front. So it really should be brought in before I start combining things. So I'm just not going to press my luck. I'm going to stop there where I think I'm ahead. Side note, if you want to remember that the integral of tan x is going to be negative natural log of the absolute value of cosine x plus c, we're probably going to use that about 3 more times in the course. If this is something that you think is worthwhile to memorize for those 3 times, rock on, commit it to memory. If it's not something you want to waste your memory on, you are welcome to redo all this math the next 3 times that we encounter that. It's 100% up to you. Alright, so this guy's a little bit messier. Again, I'm going to pick my denominator to be u, just because that's where u likes to live. I'm a little bit worried that I might have tripped over something here, so it might be worthwhile to solve this and see if I can get a cosine value of x that would make this denominator equal 0, and see if that's less than pi over 3. I'll leave that to you to explore if you're worried. So negative 4 cosine x is going to become 4 sine x dx. dx equals du over 4 sine x. And my problem becomes 0 to pi over 3 of 4 sine x over u times du over 4 sine x. Well, look at that. It's a perfect match. They cross each other out. I've got my classic 1 over u du, so I'm going to turn that into the natural log of the absolute value of u, going from 0 to pi over 3. Natural log of the absolute value of 1 minus 4 cosine x, going from 0 to pi over 3. Alright, so I plug a pi over 3 into that. And again, I think that's root 3 over 2. So root 3 over 2 times 4 is going to be 2 root 3. Now I've got the natural log of the absolute value of 1 minus 2 root 3, which is a negative number, minus cosine of 0 is going to be 1. 1 minus 4 is negative 3. Turned positive is 3. Again, optionally, if I want to combine this together, I could say 1 minus 2 root 3 all over 3 inside the natural log. And that's my answer. So ultimately, all we're doing is playing around with a new skill. We now know how to deal with fractions. Once you know how to deal with fractions, you can just apply the natural log rule, and now you can handle a larger variety of integral problems. Come test time, come final time, I'm not going to tell you you're supposed to use the natural log. You're just supposed to be comfortable analyzing when it's appropriate. All right, enjoy.